So I'm going to talk about Northern Lights, turbulence, and rocket scientists. So are you ready for the launch? For a countdown?
7, 6, 5, 4, 3, 2, 1.
This is our rocket that we launched 19th of February this year. And we launched it from Andoya. You can see the Andoya. It went up, the rocket spins to be stabilized, and then it ejects the engine, ejects the cone, and removes the payload and some small booms. And on these booms, we have our instruments. So that's how it looks like. This is one event. You are waiting for this countdown. You are waiting 2 weeks to press the button. And finally, when you press the button, you get 10 minutes of measurements. And that's how it looks like. I mean, with almost a selfie. But what do we do? Why do we go to space? What do we measure there? Is it really something there, or is it empty? So when you think of space, you think of emptiness. And sometimes we fly so high, like 300 kilometers, 600 kilometers even, that you can maybe meet a lonely astronaut there. And that's because that's the altitude of the International Space Station. So we meet the astronauts, we meet the satellites, but is it empty? Is it vacuum? No, it is not. And then let us look a bit closer into the space. And in our solar system, we need to look on the sun. The sun is the energy source, is the source of energy and a source of the problems also for the Earth. It's a big gas sphere that it's so hot that it ionizes the gas. So in the end, the temperatures are so high that the atoms are not atoms anymore. They are becoming ionized, and you get the plasma state. So we have the 4 states of matters. You have the solid, that's over here. You get the liquid, then you get the gas. And when you insert a lot of energy and heat into the gas, then the electrons are not longer bound to the atoms, bound to the ions, nucleus, and they are free. So this kind of gas, the plasma gas, can conduct the electricity. But when we look into the sun is very energetic. It has a huge temperature and emits a lot of energy, but it's also very violent. It's very turbulent, and you can see it over here. Here is the Solar Dynamic Observatory images or movies of the eruptions on the solar surface. You can see that this is the surface of the sun. This is the plasma. This is the very hot gas that is being ejected all the time, constantly towards the Earth. And so you also can see there's a lot of vortices, a lot of dynamics on the surface. There's a lot of magnetic field included into this plasma flow. So what will happen when we put also the Earth into this picture? So on the left-hand side, we got the sun, the very hot gas star, and then we got the tiny Earth that the atmosphere of the sun is interacting with. So let us look a little bit closer into that. So in this movie, you can see that we are now surfing on the surface of the sun, and then the sun is constantly ejecting electrons and ions into the space, into the vacuum. And now and then it has even the huge eruptions. And all this material from this sun is going towards the Earth in the form of solar wind. And then fortunately we got the magnetic field that shields us from these high energetic particles. But these particles, they can travel along the magnetic field lines, and then they can get down to the ionosphere and collide with neutral oxygen and nitrogen and create the aurora. That's the reason why we can see the aurora only in the northern part of Norway. Again, you can see the aurora here. Look at these beautiful images, but look also that it's very turbulent. It's very dynamic. You can see some waves, and they are not really regular. And this is the trace of this high energetic particles from the sun that are coming down to the atmosphere. It's happening on 200 kilometers, 150 a bit, and higher up. But it still can affect us on the ground. But it's also very turbulent. The turbulence is a very general problem. It's a most fundamental problem in classical physics that has not been unsolved. And you can encounter turbulence in everyday life. You just pour milk into your coffee cup in the morning, and then you can observe it. But at the same time, you can see that there's a lot of different structures, interacting structures of different scales. It can be the fluid. You can see it in the atmosphere, in the clouds. When you sit in the sunny day and watch the cumulus clouds, they are just bubbling, bubbling, and bubbling. So there's a lot of things happening. And this is the same what is happening with the aurora in the ionosphere, but we just cannot see it that well. The only manifestation is the aurora. So when we think of the aurora, we are thinking of these nice pictures, beautiful, tourism, and so on, but for us, it's something more. It's all the space weather that is behind it. When we have the high activity of the sun, especially, then we can have the lot of particles precipitating, going towards the Earth. They can damage the satellites. It happened many times. It's a big issue for the astronauts' safety. They cannot go out and wander into the space when we have the big solar storms. In the ionosphere, when we have the high activity in the ionosphere, then this ionized gas, as I said, it can carry electric current. And this electric current can then in turn induce the currents in the Earth. These currents in the Earth can break down the electricity grid. It has happened many times before we learned that it's possible. And this is the threat. This is a problem for telecommunication, for cables, for disruption of the communication. This is the problem for the this is the problem for the flights, for the passenger, for the pilots. They cannot communicate with the ground. And at the same time, the structures, all these turbulent structures in the ionosphere, they prohibit or they destroy the communication with the satellites. And the communication with the satellites is something that our society relies more and more on nowadays. And it's everywhere. We are basically bound to space. We cannot get rid of it anymore. And now you can think of the search and rescue operation in the north, the shipping in the north, in the northern latitudes, the drilling where you need to have the high precision drilling in the north. So you don't want to have the spill in the Arctic, oil spill in the Arctic. And then, of course, the aviation safety. All this is connected to the satellites. But in between the satellites, we have the ionosphere. And this is in particular important for us in the north. Here you can see the picture of the typical aurora oval. Sometimes it expands as far south as Oslo. And then we can see the aurora from here even. It's a ring, it's a donut shape around the poles, around the magnetic pole. And this actually poses problems for the aviation companies because, and also for positioning systems, because then when you have all the satellites that provide the signal to your GPS when you walk in the mountains, sometimes you get the structures, ionosphere structures, the plasma bubbles, the plasma irregularities. You can have the ranging error, you can just cut the signal from the satellite. So you need to be quite accurate. When you are really relying on this so much. So for us, we want to study the ionosphere, because the ionosphere is the answer, provides the answer how to actually mitigate for this process, how to counteract this process, when to say to the pilots, okay, be careful, don't fly over the poles. And actually, recently, many of our members of our group have traveled from Canada back to Europe, and then we could see on the screen that the initial pattern of the flight was deviated. And I was sitting on the left side, right next to the window, and I was thinking, oh, there will be an aurora. And there was a magnificent aurora for about 2 or 3 hours. We were just flying below or south of the aurora. The pilots, they don't want to fly under. They are directed southward. That means it's more costly business. And so how can you study this ionosphere? How can you understand the influence it has on our society? You can use the satellites. We are actually using satellites, cluster, swarm, ACE, but we are flying high above the interesting layer. And then we need to extrapolate the data. We need to go down to the ionosphere. On the other hand, we have a network of ground-based instruments, like IceCat radars, on Svalbard, around Tromsø, super Darn radars. Then we have a new one on Svalbard now. And optical instruments where we actually can look at the aurora, how it changes in time and in the latitude. But the ionosphere is in between. And that's a problem. Because it's like looking at the top of the mountain and not knowing whether it's a stone or a person. You really need to get closer. You really need to get to the top of the mountain to see what is really happening there. And it turns out that the only way to understand it, to address this problem, is to fly the rocket. And this is what we are doing. We are launching the rocket into the ionosphere and into the Northern Lights. At the University of Oslo, we have established the Strategic Research Initiative for this space. And we have realized that launching a single rocket through this medium it does not provide the answer. We are talking about the turbulence. We are talking about three-dimensional problems. And now when you launch a single rocket, then it's actually making a single-point measurement. It's just like cutting through the medium. It will not give you much answers. So that's why we call ourselves 4D space, because we need to investigate the ionosphere in 3 dimensions as well as in time. So we actually have 3D plus time. And what we are doing is we are working towards multi-scale studies of ionospheric and space plasma structures, waves, and turbulence in the ionosphere. We are 3 departments, 4 groups. So it's the Department of Physics, Space and Plasma Physics, Electronics group. We have involved the Department of Mathematics, the experts on turbulence. We have involved the Department of Informatics, where they're building a very small structure, electronics, nanoelectronics. And we are in total about 40 people, including students, as well as electronic lab and mechanical workshop. And of course, we need to work in the national and within the national international partner network. The 4D measurements can be realized by combining all this ground-based instrumentation, the radars, optical instruments, satellite missions, as well as 3-dimensional rocket launches. But what do we mean about 3-dimensional rocket launches? I will come to that point in the next slides. But the rocket itself, it's basically a big chunk of metal on a huge amount of explosives. And this is how it looks like. This is the payload. You can see the scale. this is on the launch pad at Andoya, and there is the engine. There's a two-stage engine here. The payload the diameter is about 3 meters. It's 140 kilograms. So only this part is 140 kilograms. And we can fly as high as 350 kilometers in this IC-4 rocket that you see in the launch of. And it's about 10 minutes when we fly through all these turbulent structures that we analyze afterwards. But on top of this payload, we actually put a very small instruments on the booms. So on this huge payload, we put so small needle probes. And these small needle probes, multi-needle Langmuir probes, they collect electrons and they can tell us about the structures in the plasma density. We have had this successful launch through the Norwegian Northern Light, as you can see here. So we are flying through the Norwegian Northern Lights, but at the same time we get the polar cap patches, the electron clouds that are coming over the pole from Americas. And then when they connect, when they combine, it creates a lot of scintillation and a problem for GPS. This has been tracked. We actually include ground-based instrumentation. This has been tracked, these clouds have been tracked by the ASCAT radar on Svalbard. And here we are launching from Andoya, so we actually had to wait and get the green light from the students actually who were operating ISCAT, so we include students also, and then we launched the rocket. That launch was very successful. We have had a lot of data. This is how the data, typical data from the rocket looks like, and this is the instrument that I was talking about. And here you can see that we are going through different structures in the plasma density, which we can further analyze. So, for example, here we have taken the spectra. We are looking on the different frequencies to identify if there are any waves and turbulence. And here are different slopes of the spectra. And you can see that if we have very turbulent area, very rough area, we have the double cascade. And I will not go into details here, but the turbulence is often studied by the spectra, where you have the energy cascade from the large scales to smaller scales. And by studying this, we can understand what are the processes behind behind these structures, compare it with the theory. So we go further. So this is a new concept. This is launching the sub-payloads from the rocket. And we are going to do that next year, in July, June, July. So to go further, not to have the one-dimensional measurements, we want to have 3 dimensions. So we're actually we are going to eject daughter payloads that will have their own instruments. They will communicate with the mother. So this is the mother now. And then you had the daughters. And they will provide very detailed measurements of the 3-dimensional space. This is a very new concept. There's a lot of challenges. And we are now working on the daughter payloads. They actually look different at the moment. They are much smaller and much more compact. But there's ongoing work on the design and communication, how to communicate. We also need to work towards radiation-hardened integrated circuits to be really good when it comes to the radiation. And we have to miniaturize everything. So it's miniaturization. This is the nanoelectronics that is becoming important. But space has no limits. So we also go further. We go to space. And we have put our instruments on different satellites. These probes have been proven to be so good that we have now built 11 sets. That means 44 needles that will fly on 11 of 50 QB50 satellites that will be launched soon by it's a European project. And we are also launching our probes on the Norwegian satellite, NordSat-N, the first scientific satellite that will have a scientific payload that will be launched soon. And we have already delivered that. But we are also involved in a larger project. So we have our competence that we put into instruments from on Rosetta. So we are actually now orbiting the comet. And on a cluster where we have very sophisticated measurements for large-scale turbulence. So for this space, we fly high into the turbulence space and hope to address and explain some of the problems, advance the knowledge, advance the technology, and provide some interesting outputs for the society. Thank you.
Thank you, Wojciech. Kristin.
Very exciting speech. I was just wondering, what do you need to surveillance to make a software that could correct the interference with the satellites?
Yeah, what we are aiming towards is to have to provide this little but important indices, like by understanding what are the process behind the turbulence in the ionosphere, we can then create these indices by putting our instruments on satellites. And then we actually need to have this weather stations, right? And it's an ongoing process. It's a like global project. So we need a global network, but we also, especially the northern part, is the most complicated. So it's a question that we'll answer in 10 years maybe. Yeah.
I was just wondering if it introduces any specific problems launching rockets through interference like this. Like, I guess you use GPS and stuff for launching rockets regularly, but that won't work for you, will it?
Yeah, but at the same time, we have the very accurate launch conditions. So the rocket, when it's launched, then it's a ballistic motion. So we can calculate it. We can take into account the winds. At the same time, we use a different bandwidth. So we use a different wavelength. So the GPS, for example, is using a different frequency, and the different frequencies are affected differently by the ionosphere.
Thank you for this. I'll never look at the northern lights in the same way anymore. So thank you. It's not only beautiful. I was just wondering, have you learned anything new after you sent out about the ionosphere, after you sent out the rocket? Or is it too early to say something?
The new thing that we are going to do now is to launch the rocket with the daughter payloads. So this is the major advancement. But we have like 10 years plan. We want to send more and more daughters. We want to make them smaller and smaller. So in the end, it's like flying the rocket and just shooting a lot of small instruments. But there's a huge challenges when it comes to communication, localization, to say where they are, how to analyze this data. So we have actually people working on these problems already now because we are thinking ahead. But that's the future of all space missions. We need to have multi-spacecraft measurements. So the recent missions, they focus more and more on multi-instruments, multi-payloads, when you want to look at these three-dimensional problems, like turbulence.
Thank you very much, Wojciech.
Thank you.